See, the last class was completed, the Maxwell's equation. Now, today, this class, we are going to discuss about the Poisson's and Laplace equations. The Poisson's equation and along with the Laplace equation. Okay, so based upon this, the Poisson equation, we have to derive with that the Laplace equation. Now, this from the Gauss law, already we know discussed about for the Gauss law. From the Gauss law in the point form, the Poisson's equation can be derived. Consider the Gauss law in the point form. So that Gauss law can be treated as already we have discussed. Can be treated as otherwise the Gauss law can be named as either point form of Gauss law, otherwise differential form of an point form. So we can use any one among this Gauss law. From that Gauss law can be now here consider the Gauss law in the point form as the divergence are d. So d bar into del is equal to rho v. The point form can be mathematically expressed as inverse del or del into the inverse del into d bar is equal to rho v, where d bar is the flux density and rho v is the actually rho is charge density. In the suffix it will be mentioned if L is mentioned at the time line charge density, S is mentioned surface charge density, V mention for volume. So depending upon these situations, depending upon these situations will be considered as that rho v is volume charge density. It is known that for a homogeneous isotropic and linear medium, the flux density and the electric field intensity are directly proportional to this. D bar is equal to epsilon E bar. Now simply we can say that the equation number 2. So if you are giving that equation numbers at that time, we are not at a confused. Okay, while we are solving that or substituting one equation to in another, at that time it is very convenient for you, because often we will mention each and every one the equation number. Now this case, so from this equation 2, so already we know the form of an d bar. Just simply have to write it for this, and d bar is equal to this inverse delta into inverse of an delta into epsilon E bar is equal to rho v. Then say that equation number 3. From the gradient relationship, E bar is equal to minus del into v. So say that equation number 4. Now we need to apply these two equations, then equation 3 and 4. We have to substitute one into another. At that time the substitute 4 in 3, then we get the result of an inverse del dot epsilon minus inverse del into v is equal to rho v. Taking minus epsilon is outside as a constant, at the time the expression will be taken as that is an inverse del or a divergence, that is a divergence into divergence v is equal to minus rho v by epsilon. Now divergence to divergence operation is called del squared, so d into del simply can divergence is squared. So at that time the value is that divergence square v is equal to minus rho v by epsilon. So this is equation number 7. So this equation can be called as an Poisson's equation. This equation can be treated as Poisson's equation. If in a certain region the volume charge density is a zero, then rho b is equal to zero, which is true for dielectric medium. Then the Poisson's equation takes form. Then the divergence square equal b equal to zero for charge region. So this is a special case of a Poisson's equation, and it can be called as a Laplace equation. Simply that from the Poisson's equation the right side value keep as a zero, then we'll get the result of an Laplace equation. Okay, the equation 7 for a homogeneous medium for which is epsilon is a constant, but if epsilon is not a constant and the medium is inhomogeneous, then equation 5 must be as a Poisson's equation for homogeneous medium. Now this is for the concept of the Poisson's and Laplace equations. So still now we are completed for the first unit our topics. Okay, now we'll see that the second one or second chapter is that conductors and dielectrics. So see that once that the topics of in your units, that is an behavior of a conductors in electric field, conductors and insulators, electric field inside a dielectric material, polarization, dielectric conductors and dielectric boundary conditions, energy density in a static electric field, current density, conduction and convection current densities, Ohm's law in point form, equation of a continuity and relation between equation of continuity and point form Ohm's law and problems. Then see, before going entering into this unit, the major topics is that conductors and dielectrics. So conductors, which one is allows that current, then simply that when that can be treated as a conductors. In dielectrics or insulators can be treated as which one is the electrons doesn't flow in this material, then we can say that that is an dielectric or insulators. While these combinations of conductors and dielectrics will take over that of an insulators of these materials of conductors. These conductors will simultaneously absorb fields depending upon your field areas or field situations. So here each and everything should be in a containing an of an particular the electric field. These dielectric conductors are boundary conditions of this of an conductors. Suppose if you are mention of these conductors, these conductors will look out the entirely hospire of this the connections. Network issue. Network problem. Then see, sorry for that network interrupt. Now, these the conductors will allows the flow of a current, and dielectrics it cannot be allows. There is a major difference between those two things. Now, simultaneously will appearing for that the whole concept of these conductors will properly working of and free of electrons will flow from one area to another area. It will be continuously. Okay. The conductors is actually it will be flowing of an free electrons areas, whereas dielectrics it cannot be passed or instruct. Then some restricted reason is there. Due to that reason, it cannot be passed away from this area. So either the dielectrics will follows upon for that the material will be depends. We are designed of this that the electricity it cannot be flow. The best example we are saying that the wood it cannot be passed through any electrons. So it will be continually for this flowing. So there is no problem of this at all the conditions. Okay, now these that just what is what of an conductors and dielectrics. So simply in one word answer that conductors will take out that is a free flow of electrons in a material is called as a conductor. Dielectrics it cannot be flows. Okay, now before going to this one, the small introduction of a current and a current to density. Already we know current that is an the free which one is going to be free of electrons. The charge per unit area is called as a unit in time is called as a current. The free flow of electrons is called as a current. Simply you can define based upon your either depends upon mathematically form otherwise in general words. Okay, then see the rate of flow of electrons or charge in the sense electrons. Now the rate of charge in that case and charge is measured in amps is called as a current. The current is measured in units is amperes. Okay, now see one that key point is that appearing a current of 1 amp is said to be flowing across the surface when a charge is of an 1 coulomb is passing across the surface is 1 second. The current is considered to be motion of the positive charge. The conventional current is due to the flow of electrons which are negligibly charged. Hence, the direction of a conventional current is assumed to be opposite to the direction of a flow of electrons. Of a conventional current is assumed to be opposite to the direction of flow of electrons. The current which exists in a conductor due to drifting of electrons due to drifting of electrons is it going to the electrons will be directly considered as of this direction. Then the current which exists in the conductors due to the drifting of electrons under the influence of applied voltage is called a drift current. Then see the drifting of electrons under the influence of applied voltage. Whatever that voltage is affect or influence on drift current or electrons, then we can say that that is a drift current. While in dielectrics, there can be flow of a charges under the influence of a electric field intensity. Such a current is called displacement current or convection current. The current flowing across the capacitor through the dielectric is separating its plates in an example of a convection current. The analysis of such currents in the field theory is based on defining a current density is a point in that particular point is called field. Now, the current density is a vector quantity associated with a current and denoted as J bar. Now, uh, again that relation between I and J. Now, simply is that I is treated as a current and J is the current density. Then, both these things, what is that relation will be appearing. Now, see, consider a surface S and I is the current passing through the surface. The direction of a current is normal to the surface S and the direction of J is also normal to the surface S. Consider an incremental surface area. They are shown in below figures. Now this the area is considering that area should be covered in particular current value and as well as in this how much area is covered to that current, otherwise how many consumers are attached to this current. These are that. Then that differential current di passing through the differential surface ds is given by dot product of a current density vector j and ds. Then di is equal to j into ds, that is a dot product when j and ds are right angles together. At that time theta equal to 90. Then di is equal to j a bar n dot ds a bar n and is equal to jds. And then I is equal to integral of s j to ds, where j is equal to current to density in ampere per meter square. But if the current density j bar is a not normal to differential area, that is a differential area is ds, then the total current is obtained by integrating the incremental current, which is a dot product of j and ds bar over the surfaces. Over the surface S, this is known as the thus in general, then I is equal to integral of S j bar into ds is a dot product. Thus if j bar is an ampere per meter square and ds bar is in meter square, then that current obtained by in amperes. It may be noted that the current density is to be uniformly on AC surface to that the particular plane value. This plane value should be taken as that the current as well as the current density both are considerations will be replaced for that the original of an the free of an electrons will be passed through an drift current. Now this drift current will be to allows, because this much of current is flowing through one particular area, that area should be totally covered in entire to the field. This much of a current will be flowing. Now similarly, the relation between J and rho v, where J is that current density and rho v is that volume charge density, the set of a charged particles give rise to a charge density rho v in volume v. The velocity with which the volume charge density, that is charged particles in volume v, crosses the surface at S at a point. The velocity with which the charge is getting transferred is v bar meter per second. It is a vector quantity. To derive that relation between J and rho v, consider differential volume del v having that the charge density rho v as shown in figures. Now see these two figures, figure 5.2 and 5.3, that those figures will be indicated as an the volume consideration. The volume is that rho v, that rho v is then indicated to be along with the area to be covered, that is an del q is equal to rho v into del v. These applicable of an del v is to be an considered, then rho v into dv is directly will accepting that the value of an the rho v is the elementary charge that the volume carries, then directly then del q is equal to rho v into del v. This del v is upon for this the volume of that incremental. Now let dl is the incremental length while ds is the incremental surface. dl is that incremental length and while ds is the incremental surface. Area has incremental volume is del v is equal to del s into del L, where dq is equal to rho v del s in del L. Let the charge is moving in x direction with a velocity v bar, and the velocity has only x component of an vx. Now the velocity is denoted a small italic letter by the volume v denoted by that the small a problem is going to be done that, and hence x direction as shown by that the figure 5.3. The direction is normal to surface del S, and that the resultant current can be expressed as del I is equal to dq by dt. But now del q is the rho is that del S into del x, as the charge corresponding the length dx is moved responsible for the current di is equal to rho v into del S into del x by dt, where that del x by dt is equal to velocity in x direction, that is v. Del I is equal to rho v del s vx. Note that the vx is equal to x component of a velocity v, but di is equal to j ds when j and ds are normal. Here j and ds are normal to earth component has comparing the two components, that is an jx is equal to rho v vx is equal to x component of a g. In this case j has only x component. In general, the relation between j and rho v can be expressed as directly j is equal to rho v into v, where v is that velocity vector. Such a current is called a convection current, and the current density is called convection current density. Okay, tomorrow I will see the next class, the continuity equation. Okay, thank you.